Well, thank you very much, Professor Chairman, and good morning, ladies and gentlemen. It's my great honor to give a plenary lecture here at this important Congress. And what I'm going to talk today is some new solutions to an old problems in aeronautic industries, which was first observed in England 1 century ago. That is how to deal with the aeroelastic problems, that is flutter of aerospace structures. First of all, let me talk about aeroelastic problems. And as you know, the Wright brothers had their first successful flight test in human being history in 1903, and then they were recognized as the inventors of the first airplanes in history. However, actually, Professor Langley also had a flight test 9 days earlier than Wright brothers. However, he failed just due to some aeroelastic problems, or called aeroelastic divergence. However, at that time, nobody understood the reason why there would be the divergence and why the airplane was damaged. Then a dozen of years later, say in 1915 or in 1917, the flutter, a kind of dynamic aeroelastic problems, was observed first in England from the well-known Handley Page 1 air bomber. Actually, there are two stories about these problems. The first story said that there was a damage of a tail wing of the bomber due to the flutter in 1915. The other story said that it was the flutter between the fuselage of the airplane and the elevator. I don't know who's correct, and however, the newest version of Encyclopedia of Aerospace Engineering said the first story. Anyway, this damage stimulates the people to study the flutter or aeroelastic problems, and since then they have recognized the coupling between the aerodynamic force and the deformation of aeroplane structures. That's very important. For example, the aerodynamic force, if coupled with elastic force of the structure, will give rise to the static aeroelastic problem. That is divergence Professor Langley suffered from. And then, if the coupling among three forces, aerodynamic force, elastic force, and inertial force of the structure, then we will have the dynamic aeroelastic problems. That's a flutter. And actually, in 1920 and 1940, a great deal of efforts were made to study the mechanisms of these self-excitation. For example, the Austrian scientist Wagner and the Norwegian scientist Theodorsen reviewed self-excitation mechanisms of the flutter, and they also proposed some simple approach to compute the flutter of two-dimensional airfoils. And after the World War II, more efforts have been made to study flutter, buffeting, and gust response. Even though we still have a lot of open problems, even for the modern aircraft, here the video shows you the flutter between the external stalls and the wing. As you know, F-16 is a very well-known fighter, and even this modern fighter still suffers from the flutter problem. Well, the past 3 decades have witnessed a lot of efforts to improve the design of aircraft structures. An important major is that the design has been changed from the passive design to increase the structural stiffness to the active design to adjust the aircraft configuration. The basic idea of the active design is to adjust the configuration and mass distribution and stiffness of an aircraft according to the requirement, such as enlarge flight envelope, reduce gas response, and suppress flutter and buffeting, etc. This technique has a great potential. For example, the Air Force Office of Scientific Research in the United States launched several projects to improve those technologies. Among those projects, I would like to mention about AAW project. Here, AAW means Active Aeroelastic Wing. This project demonstrated the feasibility of those technologies to modern aircraft, then to improve the flight performance. Recent years have also witnessed some new projects. For example, in X-76A, in this aircraft, each wing had 4 control surfaces to improve the aeroelastic performance. In spite of these studies, we still have a lot of problems to realize the active flutter control or suppression in engineering. From the viewpoint of engineering science, for example, my team have done a lot of research over the past decade, and we did a successful wind tunnel test to suppress the flutter of a 2-dimensional wing section in 2005. However, we spent more than 8 years to realize the active flutter suppression for a 3-dimensional wings and then for a whole aircraft. This is the first step, that's the second step, and that's the third step. Here, the model is a B11B. J11B in China is quite similar to the Sukhoi 30 in Soviet Union. Actually, we need to solve those technical issues such as aerodynamic nonlinearity, structural nonlinearity, time delays produced by the feedback, and then we need to design the active controller under the circumstance of those nonlinearities and time delays. And finally, we need to make the wind tunnel test to validate all those approaches before they can be used in engineering. So today I'm going to talk about these 5 problems one by one. The first problem I'm going to talk is the aerodynamic nonlinearity coming from the flow, either in the case of large angle of tank or in the transonic regime. Historically speaking, there are 3 kinds of approaches to model and to compute nonlinear aerodynamic force. The first kind is based upon the work of Professor Theodorsson and Professor Lighthill. And these approaches are based upon simplified model under the assumption such as the subsonic incompressible flow or supersonic flow but moving like a piston. And under these assumptions, then we can establish a very simple model and suppose that the flow around the airfoil looks like laminated flow. And this way, we can well understand the reason why the flutter happens. However, these models can only work for very simple airfoil in 2 dimensions or very slender wings for an airplane. That's not enough in engineering. Then people develop the second kind of approach based upon the double lattice. Also works in subsonic regime, but not only for 3-dimensional wings, but also for the whole airplanes. This approach has been very useful in engineering. However, with an increase of the angle of attack or the flow speed, then the flow separation happens, and then we have vortex, just like the case in the tail of the wing, or you can see the shock wave oscillates with an oscillation of the wing, just like the video shows. In this case, we have to integrate the computational fluid dynamics and the structural computational dynamics together. Then we can accurately stimulate the interaction between the structure and the aerodynamic force. However, this gives you a lot of computational burden, and it's not possible for you to use this kind of integrated approach to simulate the interaction in aeroelastic problems, especially in the design of controllers. So people try to speed up the computation and simplify the model. That's a result of the ROM, reduced order model plus computational structure dynamics. A good example is the approach, linear approach, proposed by Hall and Dowell in Duke University a couple of years ago, based upon the proper orthogonal decomposition. However, the model is linear. It's not possible to catch up the nonlinear phenomena, such as the shock wave oscillations. Then, some other people tried to improve the results, introduce the nonlinear module. For example, Zhang and Ye in China proposed a nonlinear neural network model. That model is possible to describe and model the nonlinear interaction in aeroelastic problems. However, the model has some more parameters to be determined from the CFD simulation. But not only depends on the CFD, but sometimes also depends on the experience of the users. So that's not good. Then we will have the open problem. We will have the model either linear, with a few parameters to be determined, or nonlinear with more parameters to be determined. No matter it's linear or nonlinear, but it's determined according to a specific CFD computation. Then this way, the model is not adaptive to the change of flight conditions. So what we have done is to propose some new model that not only can catch up the nonlinear phenomenon, but also adaptive to the change of flight conditions. The basic idea is to establish a model, have the structure like this. We use the ROM, reduced order model, to replace the CFD simulation in practice. And this model actually is a recursive model, including a couple of Wiener modulars. And in each Wiener modular, we have a dynamic linear modular plus a static nonlinear modular. Here, H is a linear system of multiple input and multiple output, and F is the nonlinear static modular. And then we have some parameters to be determined according to the CFD. Then the fitting process begins from the first Wiener modular, and we put the output of the CFD into the first Wiener module, and then we calculate the residue compared with the output of the CFD. And then we put the residue into the next Wiener module, and continuously, as long as the error is too large, we need to put more Wiener modular. Otherwise, we can terminate the fitting process. This way, we can derive the specific identification procedures like this. We first identify the linear dynamic part of the first Wiener module through a robust subspace method. And then we identify the parameters in nonlinear static part. And then we put these modulars together and identify all the parameters in the first Wiener module. Then we calculate the residue output and continue the fitting process until the error is less than your criteria. Now let me give you two case studies to demonstrate this rule. The first case is to predict the transonic lift and moment of an isogai IFO proposed by NASA many years ago. In the simulation and test, we suppose that the IFO is subject to the white noise excitation in the selected range of frequency. Then this way, we will have the interaction between the structure and the aerodynamic force. Then we can calculate and can make a comparison between the ROM and the CFD. And the left two figures shows you that the result of ROM and the CFD get very good agreement. Then this confirms the validation of the approach. And the second case study is to test whether this approach is available in analysis of aeroelastic problem. Here, we let the approach to predict the flutter of the same airfoil at the flow speed of Mach 0.7 to 0.9. This is a very typical transonic regime. And the left figure shows you that the CFD results and the result from nonlinear ROM get very good agreement. However, if you use linear ROM, just like the first one proposed by Hall and Dow, then you will have an obvious discrepancy between, especially at the peak value. More important thing is that the ROM now can predict a very typical nonlinear flutter. And here we have S-shaped boundaries of flutter speed and also flutter frequency. And here, this is the result predicted by the linear model, and actually the limit circle oscillation happens just at the flow speed, much lower than the critical speed of flutter predicted by the linear model. That's a very important issue because linear circle oscillation is very dangerous in practice. Meanwhile, we made a comparison between the computation time, and here you can see that the full model requires 6.5 hours to complete the computation. However, the ROM needs less than half an hour. So that's very important. This way, the new approach can be used in engineering. As I mentioned before, this model was established under specific flight conditions. Then how comes if the flight condition changes? Then we need to let our model to be adaptive to the change or variation of the flight conditions. The basic idea is to establish a surrogate model under few sampled flight conditions. Then we predict the case of aerodynamic problems under other flight conditions by means of the nonlinear interpolation, such as the well-known cryogene interpolation. And the basic idea, the specific flow chart looks like this. We first get the data based upon the CFD computation. Then we establish a surrogate model like here, phi. Yeah, here the output y depends on the u and v. Here, u is the flight condition, including the angle of tank and also the flow speed, etc. Then we can get approximate nonlinear mapping based upon cryogene interpolation. And here, x is the vector of the state, which is changeable, and the beta is a vector of regression parameters to be fitted online step by step, and y is the output. And actually, in practice, this kind of approximate nonlinear mapping should be constructed at each time moment, step by step, and this is the whole schedule of your fitting process. And now let me show you two case studies to demonstrate the feasibility of this kind of approach. The first case study is to predict the aerodynamic load of the same airfoil I mentioned, but at different Mach numbers. That's a change of your flight conditions. And in the very beginning, we made the CFD simulation at 6 specific flight Mach numbers from 0.7 to 0.75. Then we collected the data. And then we can establish the surrogate model. And then we can predict some other the performance at some other flight conditions, such as the case of 0.725. This is just between two sampled data. And here, actually, the aerodynamic force is very different. However, the raw model get very good agreement with the CFD result. And the second case study is to predict the aeroelastic response of the same IFO at different flow speeds, but at the same Mach number. And here, we fix the Mach number at 0.725, but vary the flow speed from 0.15 to 1.25. And you can see that with an increase of the slow speed and your aerodynamic response of the airflow changes. And here, the time history is decaying. And however, here, the time history is diverging. Anyway, the results from the surrogate model get very good agreement with your CFD computation, but with very, very less cost of computation. Now let me turn to the second problem of structural nonlinearity. As you know, the backlash or clearance are unavoidable in any joint in mechanical engineering, as well as in aerospace engineering. And a lot of people have done the research regarding to how to predict, say, flutter of airplanes or wings when there is a clearance in joint. For example, such as the case in FA-18. And here, this is the elastic force of the joint, and you can see that there is about a backlash about 1 degree in rotation angle. And this is a very typical case in engineering. However, most of the studies up to now are focusing on the case, the simple case of two-dimensional wing section. And the only practical case I can find is the effect of single free play on the subsonic flutter by B about 10 years ago. So the opening problem I have to solve is how to deal with the high-dimensional problems of a three-dimensional wing, which has, for example, several thousand degrees of freedom. Meanwhile, we also have several free plays, for example, in the joint of control surface and wing, and also the joint of external stalls and the wing. The basic idea to deal with the problems of high dimension is certainly to reduce the dimension first. What we do is to introduce a number of large fixtures mass at free plays so that the wing looks like a fixed components in structural dynamics. Then we can use the model reduction, such as the Craig-Bapton technique proposed many years ago. And let me explain you why we can do the dynamic substructuring like this. And actually, for example, this is the eigenvalue problem of a single wing structure, but with free plays. For example, two free plays, one is the leading edge outboard control surface, and the other is in the trailing edge outboard surface. And then we put some fixtures mass of very large value at these two free plays. And this way, we add these items or these entries into the mass matrix. I mentioned that the mass value is very large. For example, several million times as large as other entries in the mass matrix. So this way, actually, this equation is equivalent to this simplified one because this item is too large. So we have the two cases. The first case is that the natural accuracy is positive. This way, actually, the wing is fixed at the interface between the joint of control surface and the wing. And then we have the natural eigenmodes of a wing structure, but with a fixed interface. The other case is that the natural frequency is 0. However, the mode at these interfaces are not 0. So we get the rigid body motion of the same wings, but under the assumption of the static model proposed by Craig and Babton many years ago. So this way we have approach of the dynamic substructure to greatly reduce the degrees of wings. Let me show you the performance. And here we do some subsonic flutter analysis because the transonic flutter analysis looks the same. The first case study is to predict the flutter of a wing with free plays through double lattice approach. Actually, we have 4 subcases. The first is no free play at all. The second is we have a free play in the leading edge outboard control surface. And third one is that we have free play in the other control surface. And the final subcase is that we have 2 free plays at each control surfaces. And here we made the comparison between the 4 model and the FM model. And here you can see that the predicted flutter speed looks also almost the same. Usually, you can intuitively thinking that the free play will reduce the stiffness of the whole structure. So this way, the flutter speed should be decreased. That's true in the case of tail edge outboard free play. However, in the other 2 cases, actually, the flutter speed will be a little bit higher than the case without any free play. However, should not be happy too early. Actually, this nonlinearity actually will give you some possibility of limit circle oscillation just before the flutter speed predicted by the linear model. Then the second case study gives you this example. And here, in the right figure, actually, the amplitude of the vibration of the wing will increase with an increase of the flow speed until it enters into this region of the divergence. And actually, you will have the flutter, or called limit circle oscillation, due to the nonlinearity of the backlash. So even though sometimes the backlash can increase the flutter speed predicted by the linear model, but that's not optimistic. You will have some danger of the limit circle oscillation. Okay, now let me talk about the third problem, that's delay-induced instability. And since we are going to use active control to suppress flutter, then every control loop must have time delays, say due to the digital filter or the energy transfer between your output of control and the actuator. However, usually these time delays are very short compared with the period of possible flutter, for example, only a millisecond. So in the old days, no people recognize the importance of the time delays. Also in my case, as I introduced by Professor Kang, that I did a lot of research on the time delay effect on nonlinear dynamic systems and also controlled systems. And even I wrote a book in 2001, published by Springer, talking about the time delay effect on the control performance. However, at that time, I didn't recognize that time delay is also very important in flutter control. And things changed, say, in 2005. A PhD student of mine did a wind tunnel test of a 2-dimensional wing section. And he found a very strange phenomenon. And actually, I can show you the result like this. In the very beginning, we switched off the control. Then, with an increase of the flow speed, and you can see the wing oscillate very severely. Then we switched on the control. Then the flutter should be suppressed. However, we still have some oscillation. And in time history, we found that. And here is the start of the control. And then we found that we have new oscillation with lower frequency. This is not the original flutter. That's what? Why? And we made a very detailed investigation and finally found that this is the kind of new flutter induced by the time delay of a digital filter in our control loop. And this is the experimental evidence of the delay-induced flutter in research. And almost at the same time, Professor Libresco published his numerical simulation, also emphasized that the time delay should be taken into consideration because it will give you some instability. Well, here, when I mention about the result of Professor Libresco, I would like to recall his glorious action of attacking a class of students being shut down in Virginia Tech 10 years ago, exactly, in May 2007. I suppose most of you know the story. And so in this case, I think courage is more important than academy. So Professor Libresco, even though I've never seen him, however, in my mind, he's not a good scientist, but also a hero in history. Now let me turn back to the stability analysis of a controlled system if time delays is involved. In this case, for example, we look at the simple case of FO with a lab control, but with two time delays, tau1 and tau2, introduced by the position feedback and velocity feedback. And we substitute the critical state, system state into the differential equation. Then we can get nonlinear algebraic equation. This is the eigenvalue problems. And here we use the Kronecker product to simplify the form of this eigenvalue problems. And here L is the matrix depending on the velocity. And then we can calculate, do some numeric simulation, and then to plot all the stability regions on the plane of tau1 and tau2. And here you will see, since the eigenvalue problems involves in the exponential functions, so we have infinite number of those regions, looks like many islands. And if we take 2 points, for example, A and C here, then we will have the decaying history of the dynamic response. Otherwise, if we take the point B and D outside of those islands, then we will have the divergent response of your control system. And the other case is that we need to know the effect of flow speed on those stability regions. And as you expected, that those stability regions is shrinking with an increase of the flow speed. That's very natural, and from your tuition, you can also make the same result. And then I will talk about the active flutter suppression. And the first question is that whether the conventional control strategy works. Actually, in the very beginning, people tried to design the controllers based upon, say, linear optimal theory of control. However, in practice, every controlled flutter system must involve some uncertain problems, such as the damping of your structures or time delays that I just mentioned. We must have time delay, but we don't know how long they are. And then, in this case, for example, from the viewpoint of the control people, in the community of control people, they always think that the robust control should work or work well in the case of those uncertain parameters. However, I can tell you a truth that that's not true. For example, just the wind tunnel test I mentioned in the previous slide, that when my PhD student found the peculiar phenomenon of newly introduced flutter, he tried to use flutter control to surprise the flutter, but failed. Because in this case, if you don't know the mechanisms behind your Flutter, and you only think that you have some uncertain parameters, then you use robust control, then sometimes it does not work. So in this case, we need to look at the real reason behind the phenomena. And then talking about the case, for example, if we have the control loop with a time delay like this, and we have the changeable Mach number, and then how we can design the control strategy. I will talk this problem step by step. The first one is the delayed control. Since we know we must have the control in our envelope, so how to deal with? The basic idea of mine is to introduce state transformation so that the new dynamic equation will have high dimensions but does not have time delays in control loop. We can do this. First of all, we need to discretize your dynamic equation, then get the difference equation like this, and here A bar B1 B2 W, and have the very detailed expression here. And I should mention that tau is the time delay, and here now tau may be sometimes of your sampling period Ts and plus a residue beta. Then we can introduce a linear state form like this, and x bar is the new state of the system. And then we substitute this state transformation into the difference equation. We will have a time delay free term because the dimension of the system has been increased, but the time delay disappears. As long as time delays disappear, then we can design our optimal control. For example, we substitute the state transformation into the cost function, and then we get the cost function without time delay, and then we can design an AQG based upon solving Riccati equations step by step. Then we get the delayed AQG feedback for the system when the time delay has been taken into account. And now I show you two case studies. The first one is the Flutter suppression for a three-dimensional wing with two control surfaces. And this is the schematic of the control loop. And the time delay mainly comes from the establishment of the output of your actuator, and also comes from a digital filter here. And we use two different control strategies. One is the conventional AQG, and the other is delayed AQG. And here you can see the conventional AQG. In the very beginning, it can increase the flutter speed a little bit. However, it will fail. It fails all of a sudden when the time delay approaches 14 milliseconds. However, the delayed AQG works well until the time delays has doubled this period of value. Now let me show you the second case study, and I try to show you that the delayed AQG can work in an even wide range of flutter speed. And here, the left figure shows you that AQG, conventional AQG, will get the divergent response of the controlled system at a flow speed of 42 meters per second. However, the delayed AQG works even at 46 meters per second when we have longer time delays. Okay, now let me talk about the final problems. The second part of final problems. How to design adaptive control when your flight conditions change. We start with the design procedure in the case of subsonic flutter because this is simple. In subsonic flow, when your angle of attack is not very large, you will have a linear flow. So in this case, you will have linearized control system no nonlinearity at all. So basically, since the system is linear, we can use transfer function to describe it accurately. So this way, we have the output and input ratio. That's the transfer function. And according to the transfer function, we can get the output y. And since the system is linear, and actually, we only need to update the parameter theta here, step by step, according to the variation of flight conditions. Then this way, how to design the change of theta? We suppose that the derivative of theta is proportional to both vector p and the arrow E1. And here, we let p yield a set of differential equations so as to get the performance of bounded gain forgetting estimation, which means that with an increase of time, we will forget the old things. And this way, we have two gain adaptive laws. The first is for the gain adaptive, and the second is for the parameter adaptive. And let me show you the performance of this adaptive controller. And the first case study is to validate the controller for three-dimensional wings with a tail, sorry, mistake, that's a typo, I said TEO, tailing edge output control surface. And if the flutter is not suppressed actively, actually, the open loop of the wing will be subject to flutter when the flow speed reaches 34 meters per second. Then we establish the model and update the parameters in the model with an increase of the flow speed from 30 meters per second. This way we can let our controller works, for example, until at a flow speed of 41 meters per second. This is the performance of the adaptability of the controller with an increase of your flow speed. Now let me turn to the most tough problem of my lecture today, that is the adaptive control of transonic flow. In this case, the flow is nonlinear. That I mean, the aerodynamic force is nonlinear. So we cannot use the concept of transfer functions. This way, we try to establish a nonlinear ROM first. Not only the wing, but also the surrounding flows from the CFD and CSD integration. And then we design a linear state feedback online, step by step, to suppress the transonic flutter. In the very beginning, we need to use the CFD, and this is the mesh of the fluid, and this is the mesh of the BACT wing. Here, BACT is a term of NASA called benchmark of active controlled technology. And here, the most tough thing is here, we need to use consistent mesh for the fluid surrounding your moving control surfaces. And this way, we can establish the transonic aeroelastic model, and plus the model of your actuators, we use the step motor used as an actuator. Then we have the transonic aeroobserver elastic model. However, here, both aero lifting and moment are still have very high dimensions, so we need to use nonlinear ROM to simplify this term. Otherwise, it's not possible for us to design the controllers. And to try to establish nonlinear ROM, we prefer to use simpler ROM than those I mentioned in section 2. And here, we still use a linear dynamic component. However, we use more simple nonlinear modular. Here, this is the single layer of network, only have very few neurons instead of a recursive one to get very accurate result. However, in this case, since the model has been simplified, then the linear part may have some problems just because of you do not have a recursive procedure, and meanwhile, your surface is moving. So sometimes the eigenvalue of matrix A of linear modular may be out of the unit circle. This way, we get unstable modular. If this is the case, we need to adjust the parameters of the linear model. And as soon as we have the model established, then we can design the controller. First, we identify the ROM, and also by means of the approach also called vector autorecursive with exogenous input observer. Then we design the control strategy by solving a set of Riccati equations. Then I show you two case studies regarding to this control approach. The first control approach is to predict the aeroelastic performance of transonic flutter with variation of the flow speed, say from 0.75 to 0.82. And you can see that the transonic flutter boundary can keep almost unchanged under the control. That's a very important good performance. Meanwhile, we can make a comparison between the dynamic pressure of open loop system and closed loop system. And you can see that the adaptive controller can greatly increase the dynamic pressure of your new system, which means that you have better performance or even higher flutter speed. Okay, finally, let me talk about the wind tunnel test. And I will go through quickly. And regarding to the test facilities, that's quite a standard. And we established a test rig in subsonic wind tunnel at Nanjing. And we used two accelerometers to pick up the tip acceleration of the wing. And we used the step motor to drive the control surface, either in leading edge or in the tailing edge. And before the active flutter suppression, we did three preparation tests. The first is to check the flutter speed at the case of low open loop. And according to the numerical simulation, and this wing will be subject to the flutter when the flow speed is beyond 34.5 meters per second. And you can see that's a real result. If you do not suppress the flutter all of a sudden, and actually the wing will be damaged. And the comparison gives you a very good agreement between the experimental results and the numerical results. The second preparation test is to verify the model in your computer. And actually, we did the experiment of model test online. And, but below the critical speed of flutter, for example, 26 meters per second. And this way we can get the response, frequency response functions. However, we found that actually there is a big difference between the peaks. Why? We did not take the damping of our wing into account. So according to the online test, we identify the damping and put them into the envelope, the closed loop system, then we get a good model. And third test before the flutter suppression is to check whether your actuator works well, and then you can find that we have very good following properties of our hardware. And this way we did the experiment. The first one is the delayed feedback for the flutter suppression. And here the green block gives you the time delay observer. And here I can show you the open loop and the closed loop system when they have the flutter 34 to 40. And here I show you the video of the test. And this is the single input and single output time delayed feedback. And as I mentioned, we increased flutter's flow speed from 32 meters per second. Then the wing flutters. Then we switch on the control, then it will be suppressed very quickly. And then if we switch off the feedback, then it will oscillate very severely. Show you later. So it will become very dangerous, then we switch on very soon. Okay, finally I will talk about, here is the comparison between the open loop and the closed loop. And you can see that the closed loop works much better than the open loop, of course. And finally, I'll give you the adaptive control of the system. And in this case, we can update the system parameters online step by step with a variation of your flow speed, and the yellow block gives you the adaptive controller. And here, the final result here that we have much better performance compared with the delayed feedback, because in the delayed feedback, when the flow speed reaches 39 meters per second, the oscillation will become very severely. However, in this case, we can still keep them at a not very large amplitude. Okay, now I would like to make some conclusions. First, to get active flutter suppression, we must have very good modeling, not only accurate, but also very simple, with very low dimension. Then we can design the control. And the wind tunnel tests are very important for the validation of your whole research. And as I mentioned, we spent about 8 years to realize the real performance in the wind tunnel. However, we still have a lot of open problems. For example, all the configuration of airplanes we are in our study are fixed. For example, if we have the morphing structures, then the structure varies time to time, then your model must be vary too. And this gives us a problem, how to have your ROM, reduce order ROM. That's a very tough problem. Meanwhile, the aerodynamic force changes too, and it's still also very tough work for us. And here, I found there are a lot of younger people. I hope you will focusing on those problems and realize the active flutter suppression in engineering before long. Thank you so much.